Hi there, everyone. So this is just a quick walkthrough of the dynamic programming part of Project 3. The reason that we kind of decided that we want to have one of these is that, dynamic programming is kind of scary. We never formally went over it in class. There were a lot of really helpful, blog posts linked and all that stuff, but, sometimes it just kind of helps to have someone go over it and talk to you and kind of explain it that way. So that's what I am gonna do. So let's kind of demystify what dynamic programming is, first of all, right? So dynamic programming sounds really scary, right? Because it has like a really kind of like, I think, ostentatious name, right? Like dynamic programming. That sounds so scary, right? It's terrifying. Um, but really what dynamic programming is, it's just filling out a table in a fancy order, where I will define what fancy means in a little bit. Right, so the first thing I want you all to know is all dynamic programming is filling out a table of data in some fancy order. What I mean by fancy is that whenever I fill out a certain entry of the table, I only need to look at previously filled out entries to fill out that new entry, right? So I'm kind of picking the order to fill out the table that's most efficient, right? Where I can like only need to look at previous work in order to fill in new entries of the table. So at like a million-mile view, this is all, dynamic programming is. Just filling out the table in a fancy order so that you always compute, everything you need for the next entry when it comes time to fill out that entry. So specifically for project 3, right? What is this table? Well, this table is actually going to be a two-dimensional array with the same dimensions as the picture that you're sort of seam carving through, right? So it's going to have the same width, it's going to have the same height. So this is your dynamic programming table for project 3. So great, okay. So I know dynamic programming is, it sounds really scary. It has a horrible name that like people made up in the 80s that has nothing to do with what it really is, right? All dynamic programming is, which I said a million times already, is just filling out a table in a fancy order, right? Where you always have what you need when it comes time to fill out a new entry. And for project 3 specifically, right, I'm telling you that this table, right, is a 2D array, right, that has dimensions matching the picture that we're using, right? It has the same height and it has the same width. All right, so go ahead, feel free to pause and go back if any of that was like complete gibberish to you. Don't feel bad, this stuff is really hard. But if you're with me so far, now, right, let's kind of consider what an entry, right, in this dynamic programming table actually means, right? Like if I have this 2D array, right, which is pretty much a matrix, right? If I have, for example, this x and this y in this sort of 2D dynamic programming table I'm filling out, like what does this specific coordinate here, for example, like what does this actually mean? Um, so notice, right, that this table has the same dimensions as the picture that we're seam carving on. So each one of these coordinates, like this one, right? Each one of the coordinates inside the DP table actually directly corresponds to a pixel in the original image, right? And this is pretty straightforward, right? The picture that we're carving, right, and this DP table that we're filling out here, they have the same dimensions. So it makes sense that like, one coordinate in the table corresponds directly to like a coordinate or a pixel in the image. Okay, so every coordinate in this DP table maps, right, directly to a coordinate or a pixel in the image. But what does the number here actually represent, right? Like what is that value? So it turns out that the value And stay with me because this is going to get kind of intense. It is the best cost. Another way to say that is the lowest seam energy to reach that pixel x comma y, right? So if I have this entry, right, an arbitrary entry at coordinate xy in my dp table, right, highlighted again for emphasis, right, this actually represents the lowest cost or the lowest seam energy it takes, or the lowest seam energy I can get to reach the corresponding pixel xy in my image, right? So for example, like, once I filled out this DP table and I look at like, coordinate 3 comma 2 in the DP table, that number is actually going to be the lowest seam energy or the best cost to reach, coordinate 3, 2 in the picture. That's what these entries represent. All right, so let's take a step back. We kind of learned what DP was, right? We learned what the specific table for project 3 is, and then we learned, right, like what's an entry in this table actually represent. Um, so if you're okay up to this point and you're not like horribly angry at me yet, then let's actually talk about this fancy order, right? This is where the dynamic programming magic happens. Because it turns out that this table, we can fill it out in this sort of dynamic programming way where, you pick sort of this fancy or this magic order to fill out this table so that, when you fill out the next entry in this order, you just have to look at the previous entries you filled out before. And again, that's all that DP really is, right? It's just filling out this table in a magic order so that you always have what you need to fill out the next entry. So enough yapping from me. Let's actually show an example. Cool. So this is our DP table, right? As I mentioned before, right? It has a height and a width that matches the image we are seeing carving, right? And now I'm going to give you a hint. You are going to fill this DP table out in our magic order, right, that I talked about for project 3. What that means is that you are going to fill it out column by column, left to right. And again, this is because we are finding horizontal seams, right, on the image. And again, because we're finding horizontal seams, the magic order here is filling this out column by column, right, left to right, like we see here. All right, so if we're filling this out column by column, left to right, let's think about what we have to do in this first column here, right? So in this first column, right, I am finding the lowest seam energy, right, to have a seam that reaches all of these pixels in the leftmost or the first column of the image here, right? Well, this is actually pretty straightforward, or as straightforward as anything in dynamic programming can be, right? So in this first column, we're going to call that column 0 over here. There are no pixels, right, that come like before these pixels in the seam, right? All of these pixels in column 0, the leftmost column, they are the first pixels in any seam, right, that could start in the image. So there's actually no pixels that come before them that we have to worry about. So the best energy, right, and this is a special case, but the best energy to reach any of these pixels over here in this first column, to find out that best energy, that best cost, you just have to look, right? You just have to look at that pixel's energy, right? Right, and again, that's because, in order to find the best cost to reach, for example, this pixel here in the first column, there's nothing that can come before this first pixel, right, in a scene that you're building from left to right across the image. So you just do your like f dot apply or whatever, right? And you get the energy of this specific pixel, and then that pixel energy is stored at that coordinate, right? And then you do that for the entire first or leftmost column of the image. That's kind of your initialization. You're kind of getting the ball rolling on this dynamic programming table. All right, so feel free to pause, soak that in, post on it if you have questions about why this is for the very first or leftmost column. But let's say that you believe me, right? I haven't made you horribly, horribly angry yet. So once we've actually set up the first, leftmost column, which we're going to call column 0 over here, once we've set this up by just, getting each of these pixel energies in the column, then filling out the rest of the table actually becomes pretty straightforward. And this is where our magic dynamic programming order comes in, and it's going to be awesome, I promise. So let's consider column 1. And really, you're going to do this for any other column you fill out, because you're going to be filling these out left to right, column by column, like I said. So what works for column 1 is going to work for column 2, and then so on and so forth. So let's say I'm filling out this specific entry in column 1, right? Again, the magic order here is to fill out each of these columns left to right. So if I'm filling out this specific entry in column 1, the second column, right? What do I actually need, right? Like what information do I need to know to actually fill out this entry, this specific one right here? Well, let's actually keep track of it. I need to know actually two things, right? First, I need the energy at this pixel, which is like pretty straightforward, right? I can just call my energy function on this specific coordinate of the image, and that gives me 0.1 over here. So that's already, pretty straightforward to get. Or relatively more straightforward, I should say. Nothing's easy in 373. All right, cool. So I know I can get the energy at this specific pixel. Well, I'm almost done, right? All I need to do now, and this is where the magic order comes in, is I just need to look at the 3 neighbors of this pixel in the previous column, right? Because, what's going to be the best cost or the best energy to reach this pixel? It's the energy of this pixel plus the lowest cost or the lowest energy to reach any of its 3 neighbors, right? So this is where like the magic order comes in. I only need to look at these 3 previous neighbors in the previous column here. And that, together with the energy at this pixel, tells me what actually goes at this entry of my dynamic programming table. Right, so just to kind of soak that in, I already know the energy at that pixel, and I just need to then find the minimum energy among the previous neighbors in the previous row. Pardon me, in the previous column. Right? Because we're filling this out column by column, left to right. But yeah, that's pretty much it. Each time you fill out an entry in a column, because of the order that we've picked to fill out the columns, right, left to right, all I have to do is like look at the coordinate, look at that coordinate in the image, find its energy, and then in my DP table, right, just look at the, entries, right, for all the neighbors in the previous column. And if I add those things together, right, the minimum energy among these three potential neighbors, and then the energy cost at this coordinate of the image, that tells me what actually goes in this coordinate of my table, right? And again, this is part of our like magic DP order. All you need to know, right, to compute the best cost or the lowest energy to get to this pixel, right, is just what the energy is at this pixel and what the lowest energy is to reach one of its neighbors. That's why this DP order works, and that's why it's so magical. Each time you fill out a column, you just need to look back into the previous column. So for example, to kind of clean this up, because holy cow, there's so many colors there, right? Boop, 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 boop. When I am filling out this third column, right, I'm just going to have to look at the entries in this column here. And this pattern is going to repeat until eventually I filled out the entire table, column by column, left to right. So that's how you fill out the dynamic programming table in Project 3.